So yeah, the plan is for today is to talk about spatial prioritisation of natural flood management, kind of with a bit of a focus on using SCIMAP-Flood as a tool to support that process. We're going to be running through what data and approaches are available to us. Harry's going to give us a bit of an intro to SCIMAP-Flood, when, why, and how to use it. And then we're going to briefly touch on other modelling approaches that are available to, and just when you might kind of want to upgrade to those other approaches. Just as a little bit of a warning, you're going to need a pen and a piece of paper for this. So if you don't have one on your desk already, then now's the moment to grab one. Right, fantastic. I think probably we'll start by Harry and I introducing ourselves. And for those of you that are here, if you want to just like drop into the chat who you are and which catchment partnership you're coming from, that would be great. We would really like to know, who's here. But I'm Alison Ferber. I'm a technical manager at the Rivers Trust. But prior to joining the Rivers Trust, I worked in flood risk management. I was working for a small consultancy in London. Oh, I think there's a few people. Okay. And I was leading on the kind of flood risk options appraisal. So that was my role. So that's my background in flood risk. Harry, do you want to introduce yourself?
Yeah. Hi, I'm Harry Shepherd with Alison in the tech team, mostly doing lots of coding and modelling work. And I come from uni. I studied maths, so stuff like SCIMAP-Flood and getting into the nitty-gritty of the models is what I'm interested in. So that's what I'm hoping to do with SCIMAP-Flood.
Fantastic. And to those of you that have just joined us, hi, we were just introducing ourselves. If you want to just drop into the chat who you are and which catchment partnership you're coming from, we'd love to hear from you. All right, so hopefully you can all see the presentation up on the screen. Shout if you can't, and let's get started. So also just to point out that this workshop is being delivered through the Catchment Partnership Support Fund as well. Okay, didn't want to turn. Right, okay, let's start off by defining some terminology. I just want to make sure that we're all kind of using the same terminology, and Harry and I will do our best to keep really straight on this. So first of all, an impact point. So an impact point, this is a point where there might have been flooding in the past or where we're concerned about flooding. So this is the point of interest within the catchment, where we want to understand the flood risk in that area. The catchment is the catchment that's upstream of that impact point. So basically any rain that falls within that catchment is going to ultimately drain through the catchment and come out at that impact point. So that's the catchment that contributes water. Now, I don't know whether hydrograph is a term that we're used to or not, but yeah, hydrograph is kind of an important concept that we're going to keep coming back to. So rainfall will land on our catchment. Some of it will then be caught and instantly, like it won't make its way to the ground even. Some of the water will infiltrate, some of it will run off, and we'll get at that impact point, we'll get a hydrograph, okay? And in really, really simplistic terms, when we're talking about flooding, the critical thing is what is that peak flow, because that's going to determine how bad our flooding is at that impact point. So let's start by defining the problem. So at the top here, let's say we've got a really natural catchment. I've made a little animation. We'll see if this works, okay? So as it starts to rain throughout the catchment, what you can see is, it takes a bit of time, but all that water will make its way through the catchment and it will flow out at this impact point here. And on the right, you can see the hydrograph that shows you the flow at that particular point in the river network. Now, for a natural catchment, the characteristics that are good, we've got quite a lot of base flow there. That's good. The catchment has quite a nice slow response. And we've got, you know, just a gentle rise and fall. So the problem that we're dealing with is, if I just show you this second catchment down here, let's make it rain again. All of the decisions, all of the land use decisions that we're making have really changed what the hydrograph looks like at that outfall point here. So with things like, particularly in our kind of urban London catchments, what you tend to see is much lower base flows in the river. The catchments tend to have a much quicker response. So the time when the rain starts to the peak of the flood is much shorter. And the flood is much more peaky. So that peak flow is higher. And remember, as we've just said, higher peak flow actually means that's a more serious flood problem. So when it comes to NFM, what we're trying to achieve, we've got this problem where water is moving too quickly through the catchment, and the objective of our natural flood management, or our NFM, is to really try to slow down that water as it's passing through the catchment. And we want to try and return the hydrograph from this state that we've created to just slow it all down, reduce the peak flows, and have a more gentle flood response from the catchment. So that's the kind of general idea, but then there's this question to do with spatial prioritization, is where in the catchment should we be spending our budgets in order to have the maximum impact? So I've just put this slide together because there are various different ways that we can try and answer that question. And what I've done is I've put them into these kind of 3 levels. So at the most kind of fundamental level, what we can do is we can review existing data layers, and we can try and identify NFM opportunities. So the tool that we might use to do that is the CaPS data package. If we want to go up to the next level, then we might do some conceptual modelling, so trying to understand the rainfall runoff processes in the catchment. And this is where SCIMAP-Flood comes in, because SCIMAP-Flood is a really useful tool for that. So we'll be talking a lot more about that in the presentation. But then if you want to go up and like to level 3, so up even more, then we might undertake full simulation modelling. So I don't know, some of you might have come across JFlow in the past. It's that kind of approach. So walking through these options from top to bottom, right, first of all, so the basic level is that we're going to review the data that's available and try and understand what we can learn about flood risk and where NFM might be, where we could implement NFM from that data. Now, I know that in the presentation last year, Dave spent quite a lot of time talking you through the data that's in the data package that relates to flooding. So I'm not going to do that again. What we've done is we've put together, if I can, I don't know if I'm going to be able to show you, let me just see. We've put together for you a little bit of a data cheat sheet. It doesn't seem to, no, it doesn't seem to want to show it. We'll circulate, what we'll do is after today, we'll circulate the data cheat sheet around to you, because what that does is that walks you through what data is available through the data through the CaPS data package, where you can find it within the data package, what that data is used for, what it can tell us, but also where its limitations are, so what it can't tell us. But just to summarize, I think there are lots of questions that we need answers to that we can start to answer just by looking at the CaPS data package. So, for example, where in our catchment is there a downstream flood risk? So, well, to answer that, we need to know where in the catchment floods, and we can use the EA flood maps for that. Where in the catchment would floods actually cause damage? Again, there are data sets that can help us out with that as well. And then where in the catchment are there opportunities to implement NFM? There's a few data sets. The kind of key one for that is the working with natural processes data sets that the EA have out. But I just want to summarize, slides don't want to turn. So just to summarize, I'd say that just by looking at the CaPS data package, we can get a feel for downstream flood risk. and we can also get a feel for NFM opportunities. And so if we identify those areas where there's both a downstream flood risk and also there's an opportunity to do something at a kind of NFM scheme, then we get this kind of NFM options long list. So those are the areas that we're kind of initially interested in. However, there's something missing from that picture, because if we kind of overlay all the areas where there's a downstream flood risk and all the areas where there's NFM opportunities, we'll find there might be quite a lot of potential areas that we could kind of target our NFM to. So the question is, how can we prioritise that a little bit more? Spoiler alert, the answer is going to be SCIMAP-Flood, but we're not quite there yet. Before we get there, what I want to do next is, this is where you need your pen and paper, because I've kind of prepared a little bit of a quiz for us. I just want to talk a little bit more about spatial prioritization theory when it comes to NFM. Okay, so first of all, in this, so the question in each of these cases is, here's a catchment. To keep it really simple, we're going to assume that that catchment's really quite homogeneous, that it's like got a fairly uniform hydrological response throughout the catchment. So the question is, you know, we've got here, as you can see from the slide at the beginning of the presentation, you can see the hydrograph that you'd get with the kind of natural catchment in the past. We've got the hydrograph as it currently is with all urbanisation that's happened in the catchment. And we're going to put an NFM intervention up here at the top. What do you think the hydrograph, what's that going to do to the hydrograph? Okay, so I'll just give you, just like not very long, just like half a minute or so to just grab a pen and paper and just sketch out what you think that's going to look like. All right, so if you've done that, I'm going to make it rain and we'll see how your answer compares. So it starts to rain all over the catchment. And this solid red line coming up here is showing what the hydrograph is going to look like after the NFM implementation. I don't know if you got your answer right or wrong, but because the NFM is right at the top of the catchment, this part of the catchment is, because we've got a really uniform catchment, it's going to come through the catchment last. So it's really only having an impact on the tail of the hydrograph, and it's having quite a small limited impact as well. So because we've just focused at the top of the catchment, the answer is that is not, in terms of like the effectiveness of solving the flood problem, that's not very effective. Okay, we'll do the same thing with this next one. What happens if instead of putting the NFM up in the top of the catchment, we put lots of NFM all in the middle of the catchment? So again, I'll give you a few seconds just to scribble something down for that. Okay, I'm going to make it rain. All right, great. So this has actually had the effect that we want our NFM to have, which is that it's delayed that flood peak. So the response of the catchment is much slower. The peak is lower, which means the flooding that will occur is not so severe. So yeah, hopefully your graph looks something a little bit like that. So that is a really effective place to put NFM. Right, finally, let's just try this last one. What happens if you put the NFM right down at the bottom of the catchment? Oh, sorry, I didn't give you very long offset. Them both are. Apologies, I meant to give you a little bit longer to draw your graph. Okay, we'll wait till it's finished. So what's happened there is that we've actually, the impact that we've had with our NFM is it's had the effect of, on that first bit of water that's coming through, of slowing that down. And that's just pushed that, so it's impacted the front end of the hydrograph here, And it's delayed that water coming through, which has had the effect of actually kind of amplifying the problem of flooding. Now, this is quite a theoretical problem, but in theory it could happen. So yeah, we do need to be a little bit careful about where we're putting our NFM and the impact that that's actually having on flood risk. So of course, in those examples that we just looked at, the catchments, we were saying that only works because we're looking at really simple catchments that are really homogeneous. Now, of course, in reality, catchments are not simple and homogeneous. Catchments are really complex. There's a variety of soil types, land uses, roughnesses, and slope. And so it becomes really complicated to kind of intuitively work out where is the best place in the catchment to put the NFM. And so we need some software to be able to help us with that, and that's where SCIMAP-Flood comes into it. And yeah, just to add, another point to add is that often we within a catchment, because catchments are complex, we might be worrying about more than one impact point, and so there might be a flood point here, but another flood point that we're also concerned about a bit lower down the catchment. And that just makes the problem even more complex, and it gives us even more reason why we need to use a software for that. And I think Harry's going to talk a little bit more about that a bit later. So I'm going to hand over to Harry in a moment, but just before I do that, I just wanted to touch on the way that SCIMAP-Flood compares to other modelling, alternative modelling approaches. So SCIMAP-Flood down here, which we're calling our sort of level 2 approach to spatial planning of NFM, it's really conceptual. So if we want to go up to the next level, level 3, then we might be looking at 2D flood modelling or integrated urban drainage modelling. So 2D flood modelling, an example would be JFlow. I don't know if you've come across integrated urban drainage modelling examples as well, but the way that the level 3 models differ and go beyond what we're doing with SCIMAP-Flood is that they are actually simulation models. So they're breaking the catchment up into like really small discrete pieces, say like a kind of 5 meter into 5 meter like grid or something like that. And in each element of that grid, they're actually kind of looking at mathematically describing all the processes of the water moving through that grid. So it's like from rainfall, it's like there'll be a mathematical model to describe evapotranspiration and a mathematical model to describe infiltration and runoff. And so then the model runs, it's a simulation, it'll run in maybe like 5-minute intervals, and at every point in that whole model run, it's tracking where is the water as it passes through the catchment. So the kind of 2D flood modelling and integrated urban drainage modelling are a lot more complicated and a lot more expensive than something like SCIMAP-Flood. That's the thing to note. The difference between the kind of 2D flood modelling and the integrated urban drainage modelling. So integrated urban drainage models have the kind of 2D element, but they also include the sewer network. So what I'd say, I know a lot of you are kind of in the quite urban areas. If you're in a very urban area where the influence of the sewer network is quite important to capture, you probably want to go more for this integrated urban drainage modelling over just a kind of simple 2D flood modelling approach. But as we move up through those tiers, we get an increase in complexity and time, and so yes, they're more detailed and you might be more confident in the results, but there's also this trade-off of increasing complexity, time and cost. And the important thing to kind of keep in mind when you're planning the approach that you're going to use in your catchments is this idea of the principle of proportionality. A kind of good rule of thumb is don't spend more than about 10% of the value of the scheme on the appraisal process. That's the kind of rule of thumb that I use. So sometimes funders will require you to have one of these more complex models. But if, you know, it gets really expensive really quickly, and if your schemes just isn't valuable enough to justify that, then you might be better just stopping with something like SCIMAP-Flood. Right. Okay, Harry, I'm going to pass over to you. I'll just stop sharing my screen.
Okay. Okay, so then I'm now hopefully going to talk about, SCIMAP-Flood and then how it should fit into everything that Alison's already talked about with level 2 modeling and how that fits into your catchment planning. And I'll talk about SCIMAP-Flood not in loads of detail on the exact process, but more helping you understand your catchment in terms of model inputs and outputs. So how you can think about your catchment as the different model inputs, and then once you get your output from SCIMAP-Flood, how you can interpret that output and apply it to your catchment planning and NFM planning. Okay, so starting with what is SCIMAP-Flood. So SCIMAP-Flood is a model that identifies areas in the catchment that are most likely to contribute to peak flow at user-defined points of impact. So the peak flow being what Alison was talking about earlier with the hydrographs at the point of impact, and about how we're most interested in bringing down that peak and flattening the curve a bit. So the users will provide SCIMAP-Flood with multiple inputs that can define the catchment. And I'll go into these in more detail throughout the rest of the presentation, but introducing these are land cover, hydrologic connectivity of the catchment, rainfall patterns, so the different rainfall patterns that cause high flow events or flood events, and then travel time, so how long it takes water to move from each point in the catchment to the point of impacts or the points of impact that you've selected. SCIMAP-Flood will then use all of these inputs, and it scores every point in the catchment based on how likely that point is to contribute rainfall that will lead to a flood or a high flow event at the points of impact that you've selected. So like I said, I'll talk about these inputs in a bit more detail, but I'll just quickly talk about when you would use SCIMAP-Flood first. So for effective catchment-wide natural flood management, it's important to consider how flood events develop within the catchment. So looking catchment scale, especially for something like natural flood management, looking catchment scale is more important, is a useful kind of first step before you get into the simulation modeling that Alison was talking about, that can often be a little bit more localized. So SCIMAP-Flood will help identify how these flood events develop, and therefore it's useful when you're planning NFM schemes and interventions. And then it's also useful as it's like a piece of evidence to show communities and investors and other stakeholders in the catchment that you are delivering NFM in the best locations, and the locations that it will, you can show that it will have an impact, a positive impact. So this tool scores sites based on how effective natural flood management would be in terms of flow reduction and kind of to do with the hydrographs. So that's how this approaches natural flood management. But you might want to use it alongside other models that can explore other aspects of natural flood management. So it's good for catchment planning, but also good to go alongside other aspects of planning. Okay, so now I'll talk about the inputs in a little bit more detail. So starting by looking at the land cover map. So this map on the left is a land cover map for the catchment. There is a catchment outline. I'm not sure how well it shows on the PowerPoint. You've converted the land cover for the catchment, and then you've converted each land cover to a flood generation risk or a runoff generation risk. So this is based on the table that you can see on the right. And it's kind of similar to a runoff coefficient in that it takes a land cover and then assigns a weight to how likely that is to then pass rainfall from that land cover into the channels. And that might be based on infiltration or interception, or just how fast the water would move across the surface. So you can see in the table that urban areas, they get a score of 1. And obviously they're not always suitable for natural flood management, but they might be suitable for SUDs, so like urban drainage. But I think it's important to note now, when we look at it as an input before, because when we'll see the output, you can see that by giving then urban areas a high weight, you're saying that they contribute the most to rainfall and runoff, which is true, but you have to then make sure when you interpret the output that is about, it doesn't mean necessarily that they're the most suitable, just that they're the most they contribute the most, maybe. And now we'll move on to the next input. So then the next input is connectivity. So this is the connectivity layer, and that's been produced by there's a SCIMAP tool that's ready in a GIS software, so that can produce that for you if you just have the elevation model. And hydrological connectivity describes the ease with which water can move from one point in the catchment to another. And given that we're looking at flooding and reducing flow, that means that in this context, it's how easily rainfall can move from the point where it lands and into the river network, where it can then potentially lead to flooding and high flow downstream. And just a thing to note is that the resolution of your DEM matters quite a bit when you make this, so it's just important to think about the data that you're using when you're creating your inputs for SCIMAP-Flood. Then the next one that we'll look at is the rainfall patterns, which is now a little bit more complicated than the last two. Because if you're to choose your rainfall patterns, the first thing that you'll want to do is choose the flow events that you want the rainfall for, that makes sense. So you can see in this graph at the top of the screen, you might want to use gauge data from a gauge somewhere in your network, ideally located close to one of the impact points that you've located or that you've selected. And then you can see that there's a whole mix of peaks in this chart over time. So then what we would recommend is to use a range of flow events. So to use some really high peaks and then also some of the smaller peaks. Because if you do this, then that should give you, by selecting a range of flow events, then that should give you a range of rainfall events and rainfall patterns. And because you've then used a range of inputs, when SCIMAP at the end tells you these are the places with a high score, these are places that you should maybe look at for natural flood management interventions, you can be confident that it's used a range of rainfall patterns and flow events, and therefore those are likely to have an effect. If NFM in those sites is likely to have an effect for lots of different rainfall patterns, whereas if you use a constant rainfall or hadn't used very many rainfall patterns, then it might direct you towards some sites which are only suitable for a certain pattern. And on the SCIMAP website, they recommend using between 5 and 20 rainfall patterns so that you can get a good range of rainfall patterns. Apologies, I just keep repeating rainfall patterns over and over. You can get a range of rainfall patterns across the catchment that could, so that, yeah, I'll just repeat this, but your final output is covers a range of rainfall patterns. I'll move on from this one because I'm clearly repeating myself. Okay, so then the last one that we'll look at. Alison mentioned these impact points, and then I've mentioned them for SCIMAP-Flood as well. So when you run SCIMAP-Flood, you create travel time maps. So this is how long water takes, if it falls in the catchment, how long it takes to get from the point where it fell to an impact point. But obviously, the first thing that you need to do then is to select an impact point. You can just use one if you want to. So you might just choose to use one at the bottom of the catchment. But then you can use multiple. So for this example that I've had throughout this presentation, I've had 3 like along the spine of catchment along the main river. And then these sites where you choose, there'll probably be areas that you want to reduce flooding at. So that might be because they have a high flood risk, or also there might be a large population there if it's an urban area or some key infrastructure in the catchment. And then this one is for Oxford, or near Oxford. And I don't know that catchment well, but if you're working in your own catchments, you might have some local knowledge or some ideas in your head about where you're interested in reducing flooding at. And that local knowledge might be really useful for selecting these flood impact points. So then once you've selected your flood impact points, you then create these travel time maps. And this map that you can see on the right just shows the absolute amount of time that it takes to get from the point where the rainfall lands to the impact point. But once you input that to SCIMAP-Flood, it then scores that travel time based on how close it is to the median. So the median time it takes to get to the impact point will get a score of 1. And then as you move down the histogram and away from the median travel times, then it rescales those values to 0. So then you can see how this travel time map would link to the hydrographs that we've been looking at earlier in the presentation, and about how identifying points in the middle of the travel time, like the middle of the catchment, would have the greatest impact because you're reducing the middle of the peak, like we've seen with Alison's animations. Whereas as you move towards the bottom of the catchment or further to the top, then that's going to have less of an impact on bringing down the peak of the storm hydrograph, and therefore it has less of a weighting. One final thing to note about the travel times, though, is so this one you can't see because it's the impact point is at the bottom of the catchment. But if it was further up the catchment, then any point below there will get a score of 0 because it won't reduce flooding upstream. So if you have areas that are maybe downstream of quite a few impact points, then they might come out as scoring lower in the final output, and that's because, and we'll see this on the next slide here, that's because SCIMAP is, or the model is saying, well, they're not reducing flow for any run through of the model using an impact point upstream of it. And this will be easier to see in the next slide. I can help see it. So these are what the outputs would look like from SCIMAP-Flood, where purple is scoring lower, and then as you move through blue and green and then into red are the areas that the model has identified as scoring highly for contributing floods causing rainfall, and therefore suitable places to look at for NFM interventions, because we've identified for multiple impact points and for multiple rainfall patterns, they often contribute rainfall to high flow events. So then there's a few things that you can, so this chart on this map on the left is for 3 impact points along the middle. You can see by the red flags, whereas this one is if you were to run it using only 1 impact point. So just look at the differences in a second. But starting looking at this one on the left, you see all of this, I'll maybe turn the lazy one, it's easier. All of this down here is downstream of 2 impact points. Therefore, for every combination, also for every kind of run through of the model that's looking at these 2 impact points, this area isn't contributing anything to reducing flooding. So then when you like aggregate all of those run throughs at the end, it shows that this score's quite low. And that's why it's quite useful to run just for the single impact points as well. And then you can get kind of combine both of those outputs to get a bit more of an understanding of how the model has interpreted the different impact points, and then you can see like basically just to say that this is underweighted because it's only contributing 1. It's not to say that it won't do anything, it's just that it's being kind of dragged down because it's got upstream impact points. So then some of the other things that we can see is like up here, this is a large urban area in the catchment, and that scores quite highly. There's quite a lot of red. There's what we looked at with the land cover earlier, that urban areas can often score quite highly. And obviously this is also upstream of all 3 impact points, which only further boosts it. And then if we switch to this map, you can see the impact of the travel time maps, because the middle of the catchment has quite a lot of red in it and quite high scores. Whereas as you move to the extremes up here and down here, they're scoring a lot lower because they're further away from the impact point, or from the median travel time to the impact point. So I think just using both of these, you can see, and ideally rerunning it as well using both the other 2 impact points, you can start to see how the inputs that you've used affect the output, but then also consider how that output, what that output maybe means for planning NFM across your catchment. And there's not necessarily just a case of here's the red section, let's look there, but thinking about what this output means in terms of your real life catchment is quite important, and also in terms of your inputs, because that helps give you a better understanding. And then quickly look at the other output that you get, which is the coefficient of variance, which just shows, so SCIMAP-Flood runs for each combination of travel time map and rainfall pattern. So if you had 3 travel times and 10 rainfalls, then it would run 30 different versions. And it just shows for each point in the catchment, it takes the coefficient of variance, which is kind of a measure of how spread the data is. So you can see this one, white, is a high score and black is a low score. So the points downstream have quite a high coefficient of variance, and that's because they've got lots of times where they'll score 0, but then all the other times when they are upstream of here, they score something. So it creates kind of it creates a spread in the data. And if you run it again for just 1 impact point, then you can start to get an idea of not just whether it's upstream or downstream of an impact point affects the spread of the data, but looking at other things like maybe how does the land cover or the rainfall affect the variance in the data. You can start to see that if you only look at 1 impact point. And the ideal situation is to have a high score here, because it shows that it is likely to contribute to NFM there is likely to reduce flooding at multiple downstream impact points. and a low score on this one, because that means that there's not much spread in the data. So for every different running of the tool, it has scored well, it's scored high. So then the last thing to look at will be the next steps. So maybe some suggested things you might want to do. So you can explore the outputs in a bit more detail. Obviously, I've run through them quite quickly, but you can visualize them in other ways that might help understand. So this heat map helps you identify kind of larger areas that have big chunks of high scores in the output. So you can, rather than looking field by field, then you can look kind of rougher area, and then also changing the symbology might help you identify other places. I've talked about running SCIMAP for other variations, so using different impact points and different combinations, or just individual impact points. Then you might also look at sub-catchments, maybe run those in a higher resolution because they take less processing. And maybe if you were comfortable or thought that the suggested land cover weightings didn't fit your catchment, you might want to think about changing those and running the tool with a different land cover weighting. And then the last thing that Alison has already talked about a little bit more is using level 1 and level 3 modeling and looking at that alongside your SCIMAP output, and then you'll get an idea of how your SCIMAP-Flood work fits with all the other work that you've done and all the other data that is available. And that is my quick run through SCIMAP-Flood. So I'll pass it back to Alison now.
Perfect. Thanks, Harry. Right, I'm going to just quickly share my screen again. Just to finish off, I just want to show you this kind of summary slide that hopefully brings together everything that we've talked about. So from the CABA data package, we can find out information about downstream flood risk, and we can also find out about NFM opportunities. Hopefully that's what a lot of you are already doing in your catchment management plans when it comes to the spatial prioritisation of NFM. But what we hope to kind of convey through this presentation is that if you add SCIMAP-Flood into the mix as well, then that could also give you some really important information about where in the catchment you might be able to have the maximum impact in terms of reducing flooding. Because if any one of these three things is missing, so let's say, I don't know, we've got a downstream flood risk and maybe there's kind of like a peak flow impact, but there's not an opportunity, then there's actually no opportunity to do anything. Or if we've got peak, I don't know, downstream flood risk and NFM opportunities, but we haven't checked out the impact that the location might have on the peak flow, then we might risk having really low impact outputs, and our schemes might not have the impact that we want them to have. So what we're trying to do with this spatial prioritisation of natural flood management is find this sweet spot in the middle where there's downstream flood risk, NFM opportunity, and it's a really impactful place to put NFM features. But yeah, I'm going to kind of open it up to questions in a moment, but I think just one thing to finish is it'd be really interesting to hear from you about whether you think this is an approach that you would be interested in applying, and if so, what support we could offer you. I think the basic situation is that, you know, we can support you if you want to run SCIMAP-Flood. I think if every kind of CABA catchment partnership comes to us and asks us to run it for them, we're going to struggle. But, you know, maybe if, you know, within the sort of Thames area, if you want to club together and get somebody to run the SCIMAP-Flood for your catchments, that could be something that we could maybe support that person with a bit of training and a bit of support. So it'd be really interesting to hear what you think, and yeah, what you need from us.
And also, just to add to that, sorry, I've also developed a story map about SCIMAP-Flood, which goes into a lot more detail about SCIMAP-Flood and it's a sort of full walkthrough of the process and shows you some more outputs, and it just is this, but with a lot more detail. And I have a link that I can put in the chat.
Yeah, drop it in the chat. So we'll send we'll send some information after this that will have the presentation, the link to the data cheat sheet, and the link to Harry's excellent, if I say so, SCIMAP-Flood story map. But yeah, over to you. Any questions?